Understanding Algorithm Growth Part 3. In this video, we will learn how to classify runtimes and why we classify runtimes. We'll start the video by first answering how do we classify a runtime. This table will help us do that by first presenting a type of running time, followed by an example of that type, and a classification for that type. For example, f of n equals c times n squared. C is simply short for constant. It can be any whole number. For example, f of n could equal 2n squared. Whenever your running time is the product of a constant times the square of the input, we classify that running time as quadratic, or big O of n squared. Next, f of n equals c times n, where once again c is simply a constant. For example, f of n equals 3 times n. Whenever your running time is the product of a constant times the input, we classify that as linear, or big O of n. Next, f of n equals a constant times log of n. For example, f of n equals 5 times log base 2 of n. Anytime the running time is the product of a constant times log base 2 of n, we say that running time is logarithmic, or big O of log n. Next, f of n equals c, meaning f of n simply equals a whole number. For example, f of n equals 7. In this case, the running time will be classified as constant, or big O of 1. The reason we call it constant is because we know that the output will be the same regardless of the input size. It also should be noted that this table is ordered from top to bottom in terms of fastest growth to slowest growth, meaning quadratic running times have the fastest growth, while constant running times have the slowest growth. Now, what exactly do I mean by that? Well, to demonstrate what I mean by that, let's bring forth another table. In the first column of this table, we have the 4 classifications that we introduced in the previous table. Then in the second column, we have example running times for each classification. We have a quadratic runtime, a linear running time, a logarithmic running time, and a constant running time. And then what we're going to do next is evaluate each of these running times for different input sizes and compare them. Starting with 2. When n is equal to 2, n squared equals 4, since 2 squared is 4. Next, 10 times n will give us 20. 30 times log base 2 of n would give us 30. And for the constant running time, we'd simply get 50. So what we can take away from this first example is that when the input size is 2, the quadratic running time is fastest, the linear running time is second fastest, the logarithmic running time is third fastest, and the constant running time in this case is slowest. Now let's examine what happens when we increase the input size to 10. As you can see here, the quadratic and linear running times, which were initially the fastest ones when the input size was just 2, have now become tied for the slowest, while the constant running time is the fastest. When we increase the input size to 100, the quadratic running time becomes by far the slowest running time. Not only that, but the gap between the linear and the logarithmic running time has gotten wider. So also has the gap between the logarithmic and the constant running time. When we increase the input size to 1,000, not only is the quadratic running time still the slowest, but the gap between the quadratic and the linear running times have also widened, just like the gap between the linear and logarithmic running times have also widened, and the gap between the logarithmic and constant running times continue to widen. When we increase the input size to 10,000, these gaps just continue to get larger and larger. When we increase the input size to 100,000, the trend continues. The gaps just become larger and larger and larger. Which leads us to the most important question of this unit. Why do we classify runtimes? Imagine that you're Google, or Amazon, or Instagram, or TikTok. These companies don't work with small pieces of data. They have millions of users and billions, if not trillions, of data that they have to organize and keep up with. So if you're writing code for one of these companies and you're trying to decide which algorithms are the best ones to use for a specific task, you're not going to judge these algorithms based off how they perform on small data. You're going to judge them based off how they perform on big data, because big data is what you'll be operating on. And this table is a clear example of why that distinction matters. In this table, we saw that when the data is small, a quadratic running time can be faster than a linear running time, and a linear running time can be faster than logarithmic, and logarithmic can be faster than constant. It wasn't until the input got large that we started to see the difference. And the larger the input got, the wider and wider those gaps became. We'll close this video by discussing how to classify running times that have more than one term. Now, what do I mean by that? Consider this running time. F of n equals 7n plus 2n squared. In 7n, we have a term that, if it were by itself, we'd classify it as linear. And in 2n squared, we have a term that, if by itself, we'd classify as quadratic. So how do we classify the runtime when those two terms are added together? The answer is, we use the classification for the slowest term, which in this case is quadratic, or big O of n squared. Next example, we have 5n plus 30. Here we have a linear term in 5n and a constant term in 30. Since linear is slower than constant when it comes to big data, we classify the running time as linear, or big O of n. Next, we have 8 times log base of n plus 3n. Here we have a logarithmic term in 8 log of n and a linear term in 3n. Since linear is slower than logarithmic when it comes to big data, we classify the running time as linear, or big O of n. Next, we have 3 times n squared plus 5 times log of n. Here we have a quadratic term in 3 times n squared and a logarithmic term in 5 times log of n. Since quadratic is slower than logarithmic when it comes to big data, we classify the running time as quadratic. Next, we have 15 plus log of n. We have a constant term in 15 and a logarithmic term in log of n. Since logarithmic is slower than constant when it comes to big data, we classify the running time as logarithmic, or big O of log n. Then for our final example, we have f of n equals 25 plus 50. Two constant terms. Whenever every term in the running time has the same classification, then the running time will also share that same classification. So, since each term in this running time is constant, constant will also be the classification for the running time overall.